In the last tutorial, we used the multi-camera array microscope, the MCAM, to acquire a vibration startle response video of 96 zebrafish in a 96 well plate. In this tutorial I'm going to show you how to analyze this data by tracking the fish with our 8 key-point machine learning model, and we'll discuss the different types of data that result from this analysis. To begin, let's navigate to the MCAM data directory where we saved the vibration startle video by clicking on the hard disk icon on the left side of the screen. Here it is, titled Vibration Startle Video with the acquisition timestamp appended to the name. When we open the dataset directory, we see the image data from all cameras stored as one MP4, the returned assay dictionary, which is a copy of the protocol we used for the acquisition, and the metadata.nc file, which contains all of the information about how the MCAM acquired the video, including camera stitching information, timestamps for each frame, illumination parameters, and camera sensor information, and much more. Double-click the metadata file to open the dataset in the MCAM Viewer software. To open the zebrafish analysis panel, go to the Assays menu in the toolbar, followed by Zebrafish, and click Zebrafish Assay. At the top of the analysis panel you'll notice that the well plate is automatically detected as a 96 well plate and a machine learning tracking model has been selected appropriately. For now we'll skip the batch analysis option as we have one file to analyze, but I will be sure to cover this when we analyze the multiple phases of the visual motor response assay in one of the next tutorials. Under the heading Output Figure Selection, we will keep the default options of plot tracks and plotted tracks indicate speed, but let's also check the box for Export Labeled Video so that we can see the results of our tracking visually, and within this box, we will keep the default option of Label Skeleton. Other options for labeling are available here, but if we choose too many of them, the indicators will be on top of each other and start to crowd the visualization. It is important to note here that exporting a labeled video here takes time to generate all of the image frames again with further labels. Many people find this visualization to be useful at the beginning of experiments, so you may want to take the extra time, but once you see that the tracking is working well, you can save some processing time by not exporting this extra video, which is why we have decided not to export the video by default. Plot distance traveled is checked by default. We find that distance traveled is one of the most used metrics in zebrafish behavior analysis, so we always plot this value. You can select whether you want to show the distance traveled within every frame or every instance of measurement, or you can sum this value cumulatively, which we will keep selected for now. Next, we can select a well grouping to average together specific wells within the well plate. Options here include no grouping, averaging each row, each column, or all fish. This could be useful for your experiment, for example, if you have a concentration gradient of a chemical across the well plate and each column has a different concentration. Grouping by column, each column will automatically be averaged together in this plot. For now let's average each row together and check plot one figure so that all rows are displayed on the same set of axes, which will facilitate in comparison. The save format we will leave as PNG, and we will leave plot stimuli checked so that we can see the vibrations indicated on the plot. Next let's take a look at the advanced settings, checking that box. For most analysis these options do not need to be altered, but I do want to briefly comment on their function. Eye analysis is unchecked and we can see that it is not enabled currently. This analysis is only available with higher resolution video acquisitions, and we will cover this analysis in another tutorial segment. Export results as CSVs is pretty self-explanatory. We find most users are more comfortable interacting with spreadsheets of data output by systems rather than delving into data management using Python, so we export all data in CSV format and we include a header in these files, which includes information about the tracking model used and other parameters used in the analysis. It is generally a good idea to keep this header for future reference. Save tracking metadata saves all tracking information in a new NC file named tracking metadata following analysis, and I recommend keeping this file too. This file is what you want to use for further custom programmatic analysis. Filter anomalies and denoising are two custom filtering steps that the raw tracking data goes through after the key point locations are inferred by the machine learning model. Filter anomalies removes erroneous data based on a few criteria, and the denoising algorithm removes key point jitter between sequential frames. A thorough description of how these algorithms function is given in the MCAM user manual if you are interested in learning more. Bin data output will combine results within the defined time bin, so for example with a 1-second time bin most endpoint metrics such as distance traveled will be summed together within this period. Some metrics such as tail angle will be averaged over the time bin. For now, let's actually uncheck this box so that we can see all of the output data with raw time resolution. Finally, if your dataset has already been tracked, you can check the Reanalyze option to skip the tracking step and modify any of the other options in this panel for reanalysis. For example, if you forgot to export the labeled video for your dataset after tracking the dataset, or you want to plot distance traveled a different way, you can check this box to save time for reanalysis. It is important to note with this option that you must have saved the tracking metadata file here to reanalyze the data quickly. Once all options have been set for your analysis, click Track Zebrafish to begin the analysis. At this point I'm going to skip ahead a few minutes to the completion of analysis processing. When analysis is complete, a pop-up window will confirm that the video was successfully tracked, and we can click Open Directory to navigate to the dataset directory. Notice here below the original metadata file, we have saved the new tracking metadata NC file, and the overall results are in the results folder. Click into this folder and we can see all of the CSV file data results, the labeled composite video, the plotted tracks of all the fish, and one other folder holding the distance traveled plots. Let me quickly show you through these files. I like to first look at the plotted tracks image. This shows the path traveled by each fish over the duration of the experiment, and we chose to have a color gradient represent the fish speed, so the color here displays blue as slow, changing to red which is faster, and green is any movement over 50 mm per second. Overall, this gives a quick summary of the experiment. If plotted tracks indicate speed is not checked during analysis, the color gradient represents time of the experiment, with blue at the beginning changing to red over time. Next, let's look at the composite labeled video. Here we can see the skeleton of the fish in green overlaid on each fish. The skeleton is made up of line segments connecting the 8 key points that have been localized on the zebrafish. This visualization is a good way to make sure that tracking worked, and we can see that the skeleton fits each fish well. Next, let's look at the distance traveled plot. We chose here to average together each row, so we can see each row represented by a different color. On the x-axis, we see time in seconds, and on the y-axis distance traveled is given in millimeters. At the bottom of the plot, we can see an indication of when the vibration stimuli occurred, their frequency, and their amplitudes. Notice on the plot we can see a response to the stimuli where the fish were startled. Next, let's take a look at each of the CSV output files. For the purposes of this tutorial, we will move through these very quickly as there is so much data that a thorough user exploration will likely be required. First, the raw tracking data CSV. Contains all y and x coordinates for each of the 8 key points, for each fish labeled by well. Each row represents a time point and values are in units of meters measured from the center of the well. At the top of each CSV, we can see the header that we mentioned contains information about the software version and analysis parameters. The skeleton data shows the length and orientation angle within the frame of each line segment making up the fish skeleton. Remember, this is the green-lined overlay we saw in the labeled video. Segments here are defined by the 2 points they connect, for example from the snout to the left eye. Angle measurements are given in degrees. The fish lengths file contains the length of each fish as well as the head length and tail length. The fish length is simply the sum of these two values. Again, all lengths are given in meters here. Within the distance traveled metrics file we see both the distance traveled and speed for each fish during each time point. Speeds here are given in meters per second. Finally, we have a summary of this information in the distance traveled key metrics file yielding the total distance traveled, peak speed, and percent of frames that tracking missed, giving us a confidence score for our measurements. Overall, this machine learning tracking analysis yields immense quantities of data which can be utilized for many research purposes, and we hope you have found this tutorial useful. For further information on these points, we do recommend that you take a look at the MCAM user manual, and then if you have any further questions about zebrafish tracking, please email us at help@ramonaoptics.com. Thanks for joining us and see you in the next tutorial.